Now, coming back here, we have a equation as Vs equal to 2yf, where y is the pole pitch and f is the supply frequency, right? So the pole pitch is indirectly mentioning about the width of the poles. So from this equation, we can come to a conclusion that the speed of the machine, here it is not mentioning as speed, here speed means the velocity. The velocity of the motor is dependent upon the width of the pole or the pole pitch, right? Width of the pole and the supply frequency of a machine. Otherwise, we can say that the velocity is defined by the wavelength, right? Wavelength in the product of supply frequency. Now coming to the slip, since it is an induction motor, even though it can be a circular or it can be a linear, it is an induction motor. So definitely an induction motor will have a slip. So slip is nothing but which is the difference of the rated speed minus the running speed of a motor. So here Vs is the synchronous speed and V is the running speed of the rotor, right? So this gives you a slip value. As the linear induction motor is similar working principle for a circular induction motor, here the slip range is from again 2% to 6% to get a better efficiency. Now coming to the thrust force base equation. So here we know the formula P equal to omega T. P equal to omega T. Here omega is nothing but the velocity. So omega is nothing but the velocity. Omega in case of angular velocity for a circular induction motor, whereas here it is a linear induction motor, so it is said to be as velocity. Again, similarly, the torque is replaced by the force, that is thrust force. So F is equal to Pm divided by V, where Pm is the mechanical power developed. Here the mechanical power, since it is a induction motor, it will have some slip value. So the power developed in the rotor is nothing but 1 minus S into PR. Similarly, the velocity in the rotor is 1 minus S into Vs. So 1 minus S, 1 minus get cancelled. So the thrust force base equation is the rotor power divided by the velocity. The rotor power divided by the synchronous velocity of the linear induction motor. Now we are going to see about the thrust force much deeper with the derivation. Right. So now since it is an induction motor, so we are considering the efficiency. So induction means nothing but an AC motor. So we are considering efficiency. Otherwise, force is equal to air gap power. Here air gap power is nothing but the rotor power. So here the air gap power divided by the synchronous velocity with the product of efficiency. So efficiency, we know the formula for efficiency is output by input, and Vs is a value what we are going to design it, and then air gap power. So this value we do not know. So if we know this air gap power value and then substitute here, we can able to obtain the value of the thrust force. Right now, going to the air gap power, the air gap power is equal to 3I E cos theta. So here generally we will mention as 3 into Vi cos theta. Here we are mentioning as 3 into E cos theta. Instead of V, we are keeping as E, where V is the velocity. Sorry, V is the supply voltage given to the motor, where E is the EMF induced in the rotor, because we are discussing about the air gap power. That is the EMF which is going to induce in the rotor. We are not discussing about the stator here. We are going to discuss about the rotor power, right? So we are going to mention about the E, induced EMF. I is the current that is flowing in the machine, and then cos theta is the power factor, since it is an AC machine, and 3 indicates the supply phase, that is 3 phase. So 3 EI cos theta. Now I value we can able to derive it. So now cos theta is the power factor, and E. So we know the formula E equal to n into d phi by dt. And here n, since it is a AC machine, this d phi by dt can be replaced by phi m into omega into cos omega t. Here generally we mention as cos theta. So theta is equal to omega t. We know that one. Theta is equal to omega t. Right. So how we can saying that theta is equal to omega t, right? So that we are going for this one. We are going for this. So here we know that theta is equal to omega t. So we are mentioning. So here we know that theta is equal to omega t, right? So again, omega is equal to 2 pi f into t, right? We know that time and frequency are inversely proportional. So these two will get cancelled. So we got the value of 2 pi, right? So theta is equal to 2 pi, that is 360 degree, right? So from this we can be able to say that theta is equal to omega t. Now, so this omega can be replaced by 2 pi f. So if you want to estimate the value of the RMS, so divided the entire thing by root 2. So that this root 2 and this 2 will be cancelled. So the remaining root 2 will be available. Such that we are taking cos omega t is equal to 1 in order to estimate the value for RMS. Again here, n is nothing but number of turns per phase, and phi is the maximum flux per pole, and f is the supply frequency. Now it is an AC machine, right? It is an AC machine. So definitely AC machine means we have to consider the winding factor, right? So we are including the winding factor. So winding factor is nothing but the product of pitch factor as well as the distribution factor. Whatever may be the value of pitch factor and distribution factor, the value of Kw is mentioned as 0.956. So that is a constant value for the winding factor. So the winding factor Kw is equal to 0.956 since it is an induction motor or any AC machine. The winding factor is said to be as 0.956. And then now we are going to see a ampere conductor per meter for two primary winding, right? Two primary winding. So take it as A. A is equal to 3. 3 indicates the supply phases. We are taking here as 3 phase, and N is the number of turns, and I is the current, that is ampere. So ampere conductor. So this ampere is nothing but the current, and conductor is nothing but the number of turns. And into 2, these 2 indicates we are going for a 2 primary winding, that is double-sided linear SR. These 2 indicates the double-sided linear SR. Sorry, double-sided linear induction motor. Okay, the 2 indicates the double-sided linear induction motor, and L be the length of a machine, and L is the length of the machine. So what is this length? So in order to know the value of this length, then we have to go for the diagrams, right? So what is this length here? So consider this one as a machine. Consider this as a primary, right? And this one is said to be as the secondary, and this one is said to be as the secondary. here the length is nothing but this one, and this is said to be as and this one is the length L, right? And this one is the length L. And coming to the width, and this portion is said to be as width W. So length is so this is the length. You should not consider this one as length. So length is, this one is said to be as the length of a linear induction motor. And then now, so the length is equal to number of poles into pole pitch, right? Now, B average. Here now, B average is equal to P5 divided by L into omega. So P is nothing but number of poles, and phi m is the maximum flux density, and L is the length as we discussed now, and omega is the angular speed of a machine. Now, or angular frequency, because it is a linear machine. So generally we can say that omega equal to 2 pi n, but it is not a angular machine. It is a linear machine. So we have to say that frequency, angular frequency, because angular frequency means it is indicating the sinusoidal waveform. That is the AC machine. So it is nothing but 2 pi f, right? So now we are going to replace this one, right? So here air gap power. So we know that. So this is the formula we obtained here. E equal to root 2 n phi m pi f into k w, right? So now, since this is the one, since this is the EMF that we derived here, and now we are going to expand this EMF with this equation. So now, going to substitute this E in this equation. We are going to substitute this E in this equation, right? So the air gap power, we are going to replace this E in this equation, and we arrive this one, right? Now, and then now we are going to replace this current value. So if we come here, we are taken the ampere conductor. So it is 3 into Ni into 2 divided by L. So I value is nothing but A into L divided by 6 into N. So it is A into L divided by 6 into N. Again, we are going to replace this frequency value. We know that Vs is equal to 2y into F. Vs is equal to 2y into F, or Vs equal to lambda into F. So according with this equation, we can able to arrive this one. So F is equal to Vs divided by 2 into y. Now, this phi, with this equation of B average, average flux density, we are going to replace this flux density by this equation. So this flux by this flux density. So this equation is arrived. Now, after simplifying, this 2 will be cancelled with this one. So remaining root 2 will be available, and then this 3 and this one. So another 2 will be available. So in the denominator, 2 into root 2 will be available. So this n and this n will be cancelled, right? So this equation is now arrived. We know that previously we discussed the length is equal to number of poles into pole pitch. So P is here, Y is here. So nothing but L. So this one and this one gets cancelled. So at last we can able to arrive air gap power as pi divided by 2 into root 2 B average L into omega K omega Vs A into cos theta. So this is the value of air gap power. Still now we are not derived the equation for the thrust force. So what is the equation for the thrust force here? So the equation for the thrust force here is F is equal to efficiency in the air gap power divided by efficiency. Still now we are derived only the value for air gap power. So now we are going to substitute this air gap power in that force equation, so that we arrive this one. Force is equal to E efficiency into air gap power divided by synchronous velocity. So after substituting, we obtain this one. So force is equal to efficiency into pi divided by 2 into root 2 into V average into L into omega into kW into A, that is ampere, and then cos theta. Right? So unit of this thrust force is Newton. So that's all about your torque. That is the thrust force equation. Right? So now we are going to discuss about our equivalent circuit of a linear induction motor. Right? Equivalent circuit of a linear induction motor. Now, coming to the equivalent circuit. Coming to the equivalent circuit of a linear induction motor. So, what is the equivalent circuit? What is the equivalent circuit? So, equivalent circuit is nothing but a convenient way to represent a machine. Convenient way to represent a machine. Here, the machine is said to be as a linear induction motor. And this equivalent circuit will consist of the inductance and resistance. Inductance and resistance. Right? But some value will be variable. It is not all inductance and all resistance is not a constant value. Some resistance and some inductance will be variable value, and that variable value are the function of speed, and that variable value are the function of speed. Now, for a better understanding, we are going to consider a idealized linear induction motor. Now, if we say, now I am going to draw a resistance here. I am going to draw a resistance which is connected across the power supply. So this is the equivalent circuit for a machine which is under a standstill condition. It is not a rotating. It is under a standstill condition. So we are going to take this resistance as R. So if your resistance is connected across your power supply, then that equivalent circuit is said to be for a machine which is under a standstill condition. But this is not suits for a machine which is under running operation. Right? Suppose if a machine starts to run, what happens? The motor is now going to produce a power. The motor is now going to produce a power. So the value R is now going to be changed as R2. The value of R is now going to change as R2. But it is an induction motor. It is an induction motor. Its speed is not the synchronous speed. Its speed is less than the synchronous speed. That is, here the velocity is less than the synchronous velocity. So it will be again modified as R2 by S, that is slip. So what is the difference in the synchronous velocity minus the actual velocity of a machine? So now this is nothing but we are going to draw this R2 by S. So this R2 by S can be classified into two parameters. One is copper loss and another one is output of a motor. So copper loss. So what is this copper loss now? So coming back here, we are going to draw this R2 by S in two aspects. One is in the aspect of copper loss and then in the aspect of output of a motor. So this output of a motor is a variable one, whereas this copper loss is a constant one, and this is said to be as R2, and this one is said to be as R2 into 1 minus S whole divided by S, right? So now here the current flowing is the I2, that is the rotor current, right? So now R2 is nothing but the copper loss, which is a constant one that depends upon the I square R, right? Copper loss is nothing but the I square R, that is depends upon the current flowing and the winding as well as the resistance of the winding, and this gives nothing but the output of a machine, right? And now we are going to consider the leakage reactance. We are going to consider the leakage reactance. So here, so the leakage reactance is nothing but the symbol is X2. Leakage reactance symbol is nothing but the X2. We are going to include this leakage reactance also. Right? And this leakage reactance, the rotor current is flowing I2, and this is leakage reactance, right? Now we are going to consider, so the rotor part is going to get completed now. So the X2, R2 and R2 into X2 is the leakage reactance and R2 is the copper loss, and R2 into 1 minus S divided by S is the output of a motor, right? Now we are going to consider a finite amount of reluctance as well as MMF is going to be found in the air gap of a machine, right? Now, if you want in the air gap, flux will be available, right? So, in order to produce this flux, current is needed. In order to produce this flux, current is needed. So, as very simple. So, then the magnetizing reactance will come to the effect, right? So, now the magnetizing reactance here is and this is nothing but the magnetizing reactance, that is X M, right? And then now then the next one is power loss, right? Due to the iron part of a motor, and next is the power loss due to the iron part in the machine. So this one is said to be as the power loss due to the iron part in the machine, and it is indicated by Ri. Right? So now this one is for rotor and this one is for the air gap. Now in the beginning stage of a equivalent circuit of a linear induction motor, we mentioned that we are going to consider a idealized image, that is no loss. No loss. But now we want to estimate the practical linear induction motor equivalent circuit. So in case of practical induction motor, there will be stator also, right? Stator as well as the air gap as well as the rotor. So here the missing parameter is the stator. So the stator will be having the primary resistance as well as the reactance, right? So now this one is the primary current and take it as I or I1, and here the current flowing is the I2, that is the rotor current. So this is the equivalent circuit of a linear induction motor, right? And then now we are going to discuss about the characteristics. Now we are going to discuss about the characteristics of a linear induction motor. So coming to the characteristics of a linear induction motor, if you want to estimate the performance, if you want to estimate the performance of a linear induction motor, there is three things. One is the power factor, and another one is the efficiency, and another one is the thrust force. So these three things we have to consider in order to estimate the power factor, in order to estimate the performance of a machine. So now we are going to see about the characteristics of linear induction motor. So in the characteristics, first we are going to discuss about the performance of a linear induction motor. So as we discuss now, for the performance, we are going to consider three parameters. One is the thrust force, and another one is the efficiency, and another one is the power factor, since it is a AC machine. Otherwise, if it is a DC machine, we are not going to consider this power factor. And now, in the x-axis, nothing but the, and we are going to take the x-axis as slip. So the x-axis is nothing but the slip, and the y-axis is nothing but the three parameters. So now we are going to mention about one by one. Right? Right. So take this point as 0 for the slip, and take this point as 0.2 for the slip, and take this point as 1 for the slip. Now we are going to draw a plot for the efficiency. So if we consider the plot for efficiency, so the plot is rising like this, right? So now from this we are going to say that if slip is 0, the efficiency is increasing. If slip is 0, the efficiency is increasing. But if slip is 1, the efficiency goes on decreasing, right? So if slip increases, the efficiency is decreasing. If slip is decreasing to 0, the efficiency is increasing. So from this, we can say that slip is inversely proportional to the efficiency. Slip is inversely proportional to the efficiency. And this plot is for efficiency. Now, and next one, we are going to discuss about the power factor. So if it is a power factor, the plot will be going like this. So this is the plot for power factor. So now, if it is the plot for power factor, so see here, what happens now? Initially, the power factor is high. When slip is 0.2. When slip is 0.2, the power factor is high. When slip is nearly coming to 0, what happens to the power factor? Power factor also is going to be reduced. So why we are considering this power factor? This power factor is reduced. What happens to the performance of a machine? The performance means it got more amount of losses. So generally we have to operate with a better power factor, right? So from this we can conclude that if the slip value is goes on reducing, the power factor also is goes on reducing, right? Now, and next one is the most important one, and that is the thrust force, and that is the thrust force. So now we are going to consider this thrust force. So this is the plot for thrust force, right? And this is the plot for thrust force. If you see here, so what happens when slip is 0? What happens to the value of thrust force? The thrust force value also is 0. When slip value is slightly increasing, what happens? the thrust force value is maximum. If the slip value goes on increasing to 1, the maximum value for slip here, so the thrust force value is reduced. So now by seeing this, we have to conclude that on which operating point we can able to get a better efficiency. So I already said that if you want to get a better efficiency, we have to see on three things for a AC machine. One parameter is efficiency, another one is thrust force, another one is the power factor. So now, so this is the only point where all the three parameters is adopted. So this is the only point all the three parameters is adopted. So see here, coming to the slip also is nearly equal to 0. Coming to the efficiency and torque, the efficiency and torque also is slightly maximum. And coming to the power factor, and the power factor value also is somewhat higher, right? So this is the maximum efficiency can be achieved only at this point. Suppose there is intersection here. If you see here, only two parameters. One is thrust force, another one is the power factor. If you see here, efficiency and thrust force only is available. So all the three parameters are interlinked only at this point. So this point can be said to be as the operating point. Operating point. So at this point, we can able to get a better performance for a linear induction motor. And still some of the parameters are there to discuss for the characteristics, so that we will discuss in the next